Hi, so my goal right now is to give you some notes on photochemical smog that hopefully will help you in understanding some of this reading that you have done. This is not an easy reading. There's a lot of details. There's a lot of minutia, and it can be easy to get lost in it. So my goal here is to help you make sense of this. I strongly suggest rereading this article after watching this video, and you may want to rewind the video in parts. First, let's review really fast what the criteria pollutants are. Remember, these are local air pollutants, not global air pollutants, and in the US, these are the local air pollutants that are monitored and are regulated. There's 6 of them. Several of them aren't relevant to what we're going to be looking at today, but the ones, they are lead, carbon monoxide, SOx like SO2 or SO3, and particulate matter. These are the 4 that aren't actually relevant to this article. The other 2 criteria pollutants that are relevant to what we're looking at are ozone, O3, sorry, no subscripts on this thing, and NOx. So NOx is going to be either NO or NO2, either one of those 2 things. Again, just so that we're clear here, the ones that are relevant to what we're doing, to what we're looking at in this article, are these right here. And we're really going to be focusing on the formation of ozone and the formation of NO2 in particular, and how these things produce smog. So let's start by looking at some actual data on for San Francisco and then LA air quality. So you can see this is the Bay Area air quality forecast, and you can see this. I took this Tuesday, May 3rd, and you can see that in most of the Bay Area, the air quality is pretty good, but again, you can tell that ozone is a concern, meaning that in certain places, ozone levels are going to be high enough to start affecting sensitive populations. Interestingly, this is mostly in the east, since the winds in the Bay Area blow from the west to the east. Here's data on LA, and again, this is interesting, just looking at what things they're focusing on. Ozone measured over an 1 and an 8-hour period. They're looking at CO, another criteria pollutant. They're looking at NO2, and then they're looking at particulate matter. And we'll actually talk about particulate matter a little bit as well. Okay, so in other words, these are real things. And then last thing I want to show you, this is data showing the concentrations of these different pollutants over time, basically. So we're looking at some arbitrary scale of the pollutant measured over the time of day. Sorry, yeah, there we go. So you can see initially we start off with no or almost no pollutants. This is sort of background levels right here. Oops, background levels. And then as time goes on, we first see a spike in hydrocarbons and NO. A little bit later, NO drops and NO2 is formed. And then both of these things drop, and instead we make aldehydes and oxidants. And in particular, the main oxidant we're going to be dealing with is ozone again. So we're going to try to look at the reactions that actually make all this happen. So the first thing again that we saw was hydrocarbons and NO. The hydrocarbons come primarily from partial combustion of fuel. So in other words, instead of just making CO2 and H2O in a combustion reaction, we're making partially burned stuff. So we might get chunks of like C4H4, or more likely we get even bigger chunks of things like C10, H18. And so, in other words, partially combusted hydrocarbons. These things are still reactive. They can still combust, but they're going to combust much more slowly, and in the process, they make trouble for our air. Where does the NO come from? Remember, that's the other first thing. So where does the NO come from? Well, it comes about from this really simple reaction. This is in equilibrium. Most of the time, this arrow is way to the left, tiny bit to the right. So ordinarily the K for this value is something, I'm totally making these numbers up, but it's going to be something like 10 to the negative 10th, 10 to the negative 20th, or whatever. At high temperatures, what happens is that the reaction shifts way more to the right. K becomes something more like 1 times 10 to the negative 6th. It still favors predominant, it's still going to favor primarily the reactants, but because it gets bigger, we start to make some products as well, so that these things actually start to become noticeably, noticeable amounts. And again, this is at high temperatures specifically in the tailpipe of a car or a bus or a coal-fired power plant or a natural gas-fired power plant, whatever. So once we've made NO, what happens? One thing that starts to happen is that it reacts with just oxygen around it to make 2NO2. This isn't actually all that likely because this is a single step reaction. And if you think of what happens in a single elementary step, that would mean that we have to have 3 different things colliding simultaneously. In other words, it means this single step reaction would be termolecular and thus is not very likely. What's more likely is one of the other 2 reactions that I'm going to show you if this thing ever scrolls down. So what's more likely is that it reacts with ozone. Ozone is an unstable molecule. Remember, ozone was is another air pollutant, and so it can react and it makes NO2 and oxygen. The trouble here is we need to actually already have some amount of ozone for the NO to react with it. So this is another pollutant that it's reacting with. Thus, initially, if you just dumped solely NO in the air, you wouldn't actually make that much NO2 because you need to have some other pollutants present in order to react with it. The other thing that can happen is you can have NO react with this crap. This is peroxyl, and the relevant thing is this comes about from the breakdown of those partially combusted hydrocarbons. So partially combusted hydrocarbons. So, and remember, just to remind us from a second ago, those partially combusted hydrocarbons, the hydrocarbons themselves were one of the first things to show up. As they break down, they can react with the NO to make this NO2. And we'll ignore this for a second. So, in any case, we start making some NO2 through either of these 2 reactions, or probably to a very small amount, this reaction. Here's what happens once we make the NO2. There's several different things. First of all, what happens is it will react with UV light. That's what this is showing up here. Low wavelength, high frequency, therefore high energy light. And it breaks it apart into NO and oxygen. So you might think, what the hell? We just created NO2 from NO. Now we're undoing that process. And that's actually exactly right. It gets broken down fairly quickly after it forms. But the thing is, it also makes monatomic oxygen. Monatomic oxygen is really, really unstable, as you can imagine, because it only has a single valence electron. Because it only has 6 valence electrons, doesn't have a full octet. So monatomic oxygen immediately, here it is down here, reacts with O2 to make ozone. So this is where that ozone is largely coming from. It is from NO2 breaking down into nitrogen monoxide, and then monatomic oxygen reacting with other oxygen to make O3. This M business, you can kind of ignore. This just says that it needs something else to react with. It sort of acts as a catalyst. In fact, it acts as a catalyst. So once you make ozone, some of the ozone persists. Other ozone, again, reacts with UV light, and it makes high energy oxygen and high energy monatomic oxygen. This star just means high energy. So in other words, the oxygen atoms or oxygen molecules, the electrons are at a higher subshell. They're in an activated energy state. They're not the ground state. This immediately just returns to normal oxygen and gives off heat. But this, what it can do is it can break water down and it can make this. And this is super, super important. This looks like hydroxide, yeah? But it's not hydroxide. This is important, the distinction. Hydroxide, as you know, is an ion. It has a negative charge to it. This stuff doesn't have a negative charge. It's just sort of almost like a molecule. It's called a free radical, and the name for this particular free radical is the hydroxyl free radical. And this stuff is both nasty and really important. It's nasty, and by the way, just so we're clear, it's making 2 of these things, right? So hydroxyl itself doesn't have the 2 OH in front of it. It's just OH minus, OH with this little dot to show that there's an unpaired electron there. So OH with the dot, hydroxyl, is important because it's highly, highly reactive. It only lasts on average, lasts less than a second before it reacts with something. But it's important because it will go through and it can break down other junk in the air. So This is complicated, but here's the punchline. All these things add up together to nitrogen dioxide, that air pollutant, reacting with water to recreate nitrogen monoxide and make hydroxyl. Okay, and again, this is the thing that cleans the air. This is sort of, even though it's nastily reactive, it's useful because it breaks down other stuff that otherwise wouldn't go away. So, notice, going back to our graph, we've now created NO2. Then NO should be a little bit less because we turn some of that NO into NO2. And we have also, it's not shown here because it's really reactive, but there's hydroxyl that's theoretically floating around. So what's the hydroxyl do? This, obviously. Let's actually start at the very bottom. What happens is this. Let's do this. We'll start at the beginning here. Here's hydroxyl. It's reacting with the RCH3. All that R means is some remainder. So this is just some organic molecule. So this is typically, it's produced in partially combusted hydrocarbons. So again, when you have combustion in an engine or a factory or whatever, you'll not only make CO2, you make stuff that's, smaller fragments of hydrocarbons. That's what this is. Hydroxyl reacts with it, and it makes all these things, blah, 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 and at the end, it regenerates or the hydroxyl, OH with the lone pair. So in the process, we've broken down the partially combusted hydrocarbon into all these other things: aldehydes, hydroxyperoxyls, alkyl oxyls, peroxyalkyls. These are all things that are found in smog, and many of them are irritating to your eyes or lungs. Aldehydes are what make your eyes get red and watery in really polluted air. And you can see them down here in the overall reaction. So the overall reaction, again, is we take the partially combusted thing. Notice the hydroxyl is not here because it's a catalyst. It's reformed, but we react with oxygen, nitrogen monoxide, and it makes that nitrogen dioxide and aldehydes. So this is actually another way that we form NO2. You probably don't remember, but way back here when we were talking about how to make NO2, this was one of those ways. We take we take this thing that's formed from partially combusted hydrocarbons and we make NO2 out of it. So the moral of the story here is that once we've made that hydroxyl from ozone breaking down, once we've made the hydroxyl, that then breaks down all the hydrocarbons into simpler things and makes these aldehydes as a side effect. So hopefully this makes more sense. We started with NO. It forms NO2. The NO2 then makes ozone, and the ozone reacts with the partially combusted hydrocarbons to make aldehydes and also to regenerate more nitrogen dioxide. This is essentially what happens in a smog event, in a smoggy day. You need UV light, which is why this only happens in sunlight. The UV is required at a couple steps to break down the NO2, to break down the ozone, and it needs to be fairly warm in order for these reactions to happen at a substantial rate. You might think, why don't these hydroxyls just stick around forever? So here's how they eventually end up. They eventually will react with activated NO2 or some other stuff to make this, and then these things that are, innocuous, non-harmful. Hydrogen peroxide is a pretty strong oxidizing agent, and nitric acid is not only an acid, but it's a strong oxidizing agent. Here's just another way of looking at this. This is a complicated graph or cycle, but it also puts it all together. N2 and O2 are the starting things just found in our air. 78% air, 21% air. They react at high temperatures to make NO, and this, through one of the three mechanisms, will make NO2. Here they're just showing that one where it reacts with peroxyl, but it could also react with any of the other things that I mentioned. It could react with ozone, or less likely, it could react with oxygen in that termomolecular step. So we create NO2. The NO2 then forms ozone. The ozone breaks down because of UV light to form hydroxyl, and then this is, you can almost think of this as sort of like a separate little cycle down here. This is the cycle of breaking down hydrocarbons. The hydroxyl reacts with this hydrocarbon to make sort of a more reactive hydrocarbon, and then in turn to make this peroxyl hydrocarbon. Notice this is the same thing that's up here, so that it's showing NO reacting with this thing to make NO2. So, and then eventually we make this puppy here, which is that same aldehyde that we were talking about before. Lots and lots of steps in this process. The main ideas are that you start, that NO is the sort of the starting step in making smog, rapidly becomes NO2 and ozone, and the ozone then breaks down hydrocarbons to make aldehydes along with a bunch of other irritating air pollutants that affect human health.